Hi everyone. In this video, you're going to be learning a technique for putting together structural formulas of covalent compounds. This is going to sort of explain what's really happening when those covalent compounds are put together, what's happening with the electrons. It's also going to explain why that honk 1, 2, 3, 4 rule from the previous lesson works the way it does. So since we are, again, talking about covalent bonding, just a quick review of what that means. Covalent bonding occurs when atoms share pairs of electrons, like this. So remember, in ionic bonding, what happened was an atom would take electrons from another atom. In covalent bonding, it's a little bit more friendly. They're sharing. And also recall that this happens between non-metal atoms, so stuff in that upper right side of the periodic table, and also hydrogen. So bonding always deals with the valence electrons. So quick review of how many valence electrons we expect from each of the groups on the periodic table. So first group has 1 valence electron, represented by this 1 dot. Second group has 2. The transition metals we skip, they do have valence electrons, but some of them have 2, some of them have 3, maybe even 4. It doesn't really follow a pattern that's predictable. Then this group has 3, this group has 4, 5, 6, 7, and 8. So that tells us how many valence electrons things have in their outer layer, their outer shell. And since we're really looking at nonmetals for this, the atoms we're concerned with are pretty much these and hydrogen. So all of those we can tell how many valence electrons they have. So recall the octet rule. Most atoms want 8 valence electrons. Octet, like an octopus has 8 arms, 8 valence electrons, with the exception of hydrogen and helium. So hydrogen over here, hydrogen only wants 2. So that means hydrogen, since it has 1 valence electron, it wants 1 more. Boron right here has 3 valence electrons, so it would like to get 5 more. Carbon over here has 4, so it wants 4 more valence electrons. Nitrogen has 5, so it could use 3 more. Oxygen has 6, so it could use 2 more. And then fluorine has 7, so it could use 1 more. And then these already have 8, so they don't need any more. So that pattern should actually look familiar with our honk 1, 2, 3, 4 rule. H is for hydrogen, and we notice that hydrogen wants 1 more valence electron. O is for oxygen, and oxygen wants 2 more valence electrons. N's for nitrogen. Nitrogen wants 3 more valence electrons, and C is for carbon. Carbon wants 4 more valence electrons. So the number of times that they are bonding is the same as the number more valence electrons they want. So every time one of these forms a covalent bond, it essentially gains 1 more valence electron until it gets up to its 8. Now this wasn't part of the honk 1, 2, 3, 4 rule, but you should notice that this group right here, the halogens with fluorine, chlorine, bromine, iodine, they all want 1 more valence electron. So these will also all make 1 bond. Similarly, like sulfur here, same group as oxygen, so sulfur will also make 2 bonds. Okay. So let's discuss how do we draw these Lewis dot structures. So first, you're just going to write the symbol from the atom off the periodic table. So like if it's carbon, you'll write C, and if it's chlorine, you'll write Cl. And then imagine this carbon had like a little box around it. You don't actually draw the box, but you can put valence electrons on the top, bottom, left, or right of the box. Carbon, we know, has 4 valence electrons, and you can check that on the periodic table. So I'm going to start putting dots, and I recommend, fill in the dot a little. If you just do like a little blip, sometimes it can be hard to see that, or you might kind of lose track of how many dots you actually have. So I'd make it more of a spot than a dot, really. So I'll just go around the carbon and put in 1, 2, 3, 4 spots for the 4 valence electrons. So each one of those dots represents one of carbon's valence electrons. And the maximum you could end up putting in is 2 per side. So if you look at this chlorine, we did 1, 2, 3, 4, 5, 6, 7. So we never put like 3 on a side. All right, so now practice for you. Please, in the notes that you're following along, try to draw the Lewis dot structure for a fluorine, and go ahead and pause the video and do that. Okay, so I'll show you how to do it now. So fluorine's symbol is F, and fluorine has 7 valence electrons. When I look at where it is, it's a halogen, it has 7, so I'll do 1, 2, 3, 4, 5, 6, 7 dots. Now it doesn't really matter which side you left as the side with 1 dot. It doesn't matter because these electrons are all attached to fluorine, so it's possible to sort of, spin that fluorine around. Okay, so how do we use this to make structural formulas? The first thing you need to know is if you have a structural formula, a lot of times for these Lewis dot structure problems, you're going to have a structure where there's sort of one atom in the middle, and then there's other atoms branching off of it. So you're going to need to know, well, which one do I make the middle atom? So the rule is, generally, you put that atom that can make the largest number of bonds in the middle. So a lot of times that's going to be carbon, because we know that carbon can make 4 bonds. If you don't have a carbon in there, well, nitrogen can make 3 bonds, so can phosphorus, so that might be a good choice. If you don't have either of those, then, well, oxygen and sulfur can at least make 2, so maybe you'd pick that. Yeah, it depends on what you have. So if you have a carbon, usually you're going to be putting carbon in the middle. If you don't have a carbon, pick the next best one. You're never going to put hydrogen in the middle because that can only make 1 bond. And you're never going to put one of the halogens in the middle because those can also only make 1 bond. Right, so let's try drawing a Lewis dot structure now for F2, 2 fluorines bonded together. So in this case, I'm going to need to make 2 fluorines and give each of them their 7 dots. Now, a good thing to do right here might be to count the total number of electrons I have. I have 7 on each, so right now I have 14 electrons. When I get done with the whole Lewis dot structures, I want to make sure I still have 14 electrons. I can't lose any electrons, I can't get any new electrons. If my electron total is 14, that's how many electrons I have to work with. Next, since covalent bonding happens when electrons are shared between atoms, I'm going to take some electrons that these fluorines are going to share with each other. So usually if you've got these sort of lone electrons hanging out without a pair, we want to just take those lone electrons and bring them to the middle between the 2 fluorines to be shared electrons. So in this drawing right here now, these 2 electrons that are between the 2 fluorines, we can say that they are shared. They belong to both fluorines, so they count for both fluorines' total electrons. And remember, they all want 8. So let's count the electrons on each fluorine and see, do they have 8? This one has 1, 2, 3, 4, 5, 6, 7, 8. Yep. And this one has 1, 2, 3, 4, 5, 6, 7, 8. Because the ones in the middle count for both of them because they're shared. So now, hooray! Both fluorines have 8 valence electrons. Both fluorines are happy. So this is a successful Lewis dot structure. Now if we want to take it one more step and write the structural formula, we need to replace these shared electrons with a bond. So 2 electrons shared represent 1 bond. So instead of these dots, we replace them with a line to show that there is a bond there. And now if I want to make sure, like, okay, I remember I started with 14 electrons. Do I still have 14 electrons? Let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the line, the bond, counts for 2 electrons, so 13, 14. So yes, I still maintain my 14 electrons. Right, let's try another one. See if you can draw the Lewis dot structure for water. And actually, let's take it all the way to the structural formula. Let's actually make the structural formula for water. Okay, so you can pause and give that a try. So when I start doing this, first I need to think, okay, what ought to go in the middle? Well, hydrogens can only make 1 bond, and oxygens can make 2 bonds. Oxygen makes more. I'm going to make sure that my oxygen goes in the middle. So I wouldn't want to arrange it like that with a hydrogen in the middle. I need the oxygen to be in the middle. And then I'm going to put a hydrogen probably on either side. Need to put my valence electrons in. Hydrogen's easy, that just has 1 valence electron. Oxygen should have 6. So we'll do 1, 2, 3, 4, 5, 6, like that. And now I need to attach these hydrogens onto this oxygen. I've got some lone electrons here, so I'm going to pair those up. I'm going to pair those up. Sometimes it's easier to kind of redraw it. So now I've got a shared pair there and a shared pair there, and then these are still there. All right, so let's check my structure. Oxygen wants 8 electrons, and it's got 1, 2, 3, 4, 5, 6, 7, 8. Good. Hydrogen, remember, is an exception. It only wants 2 electrons, and each of those hydrogen has 2. Remember, these shared electrons count for both. Good. So now all I have to do is replace those shared pairs with a line to show that those are a bond. These pairs that are still on the oxygen that are not involved in a bond, these are known as lone pairs. And if it says to draw the structural formula with lone pairs, you do still need to draw those lone pairs electrons in. So that means those are valence electrons, they're on oxygen, but they're not involved in any bonding right now. They're just kind of hanging out on oxygen. Okay, let's try one more. This is CH3I. So we have 3 different types of atoms, and the first question I need to ask is which one's going to go in the middle? Carbon can make 4 bonds, hydrogen can make 1. Iodine is one of the halogens, meaning it can only make 1 bond. So carbon better be in the middle. Like usually if you have carbon, carbon's going to be in the middle. And carbon has 1, 2, 3, 4 valence electrons. Then I have 3 hydrogens and an iodine. It really doesn't matter which side I put each one on, because again, we could just spin that molecule around and it would be the same. So put on my H's with their 1 valence electrons, and then I has 7 valence electrons. So there's my setup. And then I'm going to attach everything to the carbon by making pairs. So these two can share, these two can share, these two can share, these two can share. And you know, this might actually be a good one before I put everything together to count, to make sure that I'm not losing electrons or gaining electrons. So let's see, my I has 7 valence electrons, my carbon has 4, and each hydrogen has 1, so that's 3 total. So total valence electrons I have here are 14. So gotta make sure I have 14 when I'm done. Okay, so I've decided on my pairs that I'm going to share. I'm just going to go ahead now and erase those and redraw them as shared pairs. You can just redraw the whole thing, but make it simpler. Shared pairs in between. Okay, and now I check. Does everything have the correct number of electrons? Iodine now has 1, 2, 3, 4, 5, 6, 7, 8. Okay. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Good. And each hydrogen has 1, 2. Because the hydrogens only want 2. All right, so that means that this is good. And if I wanted to make my full structural formula, I would just need to, oops, wrong thing. I just need to erase my shared pairs and replace them with lines to represent bonds. And then these lone pairs on iodine, those are still there. They're just not involved in the bonding. Right. So those were simple ones where we only needed single bonds to make everything have the correct number of electrons, which is usually 8. But what happens if you do that? You make pairs, you do the shared pairs, and you count and you realize every atom doesn't actually have 8 electrons, or 2 if it's hydrogen. The numbers are still wrong. Well, that would indicate that you might actually need a double bond. And if that still doesn't work, well, maybe you actually need a triple bond. So I'll show you an example on the next one. Let's try to draw Lewis dot structure for N2. So nitrogen. Nitrogen has 5 valence electrons. So I'll draw 2 nitrogens with 1, 2, 3, 4, 5 valence electrons each. So my total valence electrons, let's keep track of that. Say total VE is 10. Okay, so I'm going to start, there's nothing in the middle because there's only 2, and then I'm going to start like I always do, and I'm going to make a pair with those 2 valence electrons, and I'm going to go ahead and erase them and then just kind of move them into the middle. So there's a shared pair, and then I'm going to count how many valence electrons do my nitrogens have. The nitrogen on the left has 1, 2, 3, 4, 5, 6 valence electrons right now. And the nitrogen on the right also has 1, 2, 3, 4, 5, 6 valence electrons right now. So that's not 8, right? So this structure is not done because of the octet rule. They want 8, not 6. So what I'm going to need to do now is share some more electrons. We need more shared pairs. So let's take these two because they're loners as well. And then I'm going to erase them from where they are now and move those into the middle. All right, and so now I'm going to count again how many valence electrons. So this nitrogen now has 1, 2, 3, 4, 5, 6, 7. Remember, all of them in the middle count for both. So 7. This one also has 7. So we're closer, but they still don't have 8. So what am I going to need to do? Guess I'm going to need to move another pair. So I'll take those two and move them to the middle. Just erase those. And now, finally, when I count, okay, this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Yes. And the other nitrogen also has 8. So this molecule actually required 3 pairs of shared electrons or a triple bond. I can make sure I did everything right. I had 10 electrons when I started, and I still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still have 10. So if I thought I had my structure right and I counted and I somehow had like 12 electrons in there, I would have known that I did something wrong. I gained some electrons I didn't actually have. Finally, if we wanted to make this the structural formula, we would just need to replace these shared pairs with lines, and since we had 3 shared pairs, we would have 3 lines for a triple bond there. Another thing you might see, the last thing that is maybe a little more complicated, is that polyatomic ions, remember polyatomic ions from ionic bonding, those were those sort of groups of atoms that had a charge as a group. Well, those groups of atoms are covalently bonded to each other, so we can do Lewis dot structures for them too. Here's a hydroxide ion, OH negative. Since this ion has a negative charge, it has a -1 charge, that actually means that it has 1 extra electron to include in its structure. So if I'm trying to draw the Lewis dot structure for OH minus hydroxide, I can do my oxygen, which has 6 valence electrons, and I can do my hydrogen that has 1 valence electron, and then because of this negative charge, I have 1 more electron. So I just need to stick on 1 more electron. Now, you could stick it on the oxygen or you could stick it on the hydrogen. These electrons are going to be shared. So they are electrons that belong to the entire molecule. We can move them around. It's okay to move electrons around just as long as you have the right total number of electrons in there. So in this case, my total number of electrons, oxygen has 6, hydrogen has 1, and this little extra negative gives me 1. So I should have 8 total electrons in here. This negative doesn't mean that the oxygen gets an extra electron and the hydrogen gets an extra electron. It just means overall the whole molecule gets an extra electron. And then bonding this is pretty easy. I'll just share this pair and I'll go ahead and redraw it. And it turns out oxygen has 8 valence electrons, hydrogen has 2. Everything is happy. My structural formula will look like that.